Okay. In oscillations, it is the advanced form of the waves that we studied in AS. So oscillations is like, in simple words, to and fro motion, continuous disturbance. Because in waves can also be defined as the continuous disturbance in the body or in the particles. So same we can use for oscillation. So it is a like repetitive motion that has a time period. So that is called oscillation. So for definition, we can say repetitive motion that has a time period. Okay. And secondly, this is the basic definition, and there is nothing new in oscillation, but the next concept is completely different from it. That is called simple harmonic motion.
Okay.
So this is the important topic. In short form, we can say SHM.
All right. When I'm doing like question answers and stuff, like this is a really silly question, but like if I write SHM, would it be accepted instead of writing like the full form?
Try to write full form because there is like a 50-50 chance of getting full marks or not, because it is very understood term, because everybody knows about simple harmonic motion, even a student who don't know about the definition but still know the name of SHM. So if we write SHM, so that is also fine. But in exam, always like write the full form to avoid any type of misconception that will lose the marks, because simple harmonic is a long term. So in notes, mostly we write SHM. But in your final exam paper, try to write full form. Okay.
Okay.
Okay. So simple harmonic motion is also derived from the term oscillation or the waves. But we have some specific new knowledge included in simple harmonic. So first of all, it is a periodic motion, definitely. Second, the second important thing in simple harmonic motion is to write, it is a periodic motion in which acceleration of the body is directly proportional to its displacement, in which acceleration of the body is directly proportional to its displacement. And the third important point for simple harmonic motion is in opposite direction.
So like it has to go from left to right, right to left.
Yes. So, if we are actually writing the definition of simple harmonic motion, so we can even write the definition for 3 marks. But we know that for definition maximum, they usually ask for 2 marks or 1 marks minimum. So it will easily give you 2 marks. This is a complete definition, complete concept for simple
So
harmonic.
it, like simple harmonic motion is a periodic a motion in which the acceleration of body is directly proportional to displacement, but in opposite direction. So
Yes.
this is like what the marking scheme has.
Yes. This is the complete definition and complete concept of simple harmonic motion. Because when we discuss about examples, so you will get clear idea that why we are writing opposite direction and how acceleration is directly proportional, right? So
Okay, right.
according to the statement, we can say acceleration directly proportional to displacement, and we use negative sign for opposite direction, right?
Yeah.
Okay. Now, before writing further in the formulas and to explain or expand the formula, if we consider the examples in our syllabus, so the first example is spring mass system.
Spring mass constant.
So, we need to check if we use the spring mass system. So, a spring mass system is also eligible for simple harmonic motion or not, because there are different examples that perform periodic motion. Periodic motion is only one condition for simple harmonic. Second condition, acceleration must be directly proportional to displacement in opposite direction. This is also the condition for simple harmonic, right? So we are going to test that either spring mass system obeys simple harmonic motion or not. Okay. So
Okay.
first of all, if we consider a setup for spring mass system, so on the first set, we consider spring and mass in original form. So initially, this is the position of spring and mass. And this state is the original state of the body. This is original length. And there are two possibilities for this spring mass system. Either we can shift this body towards positive side, like we can stretch it, or the other possibility, compress it towards negative side. Okay.
Okay.
And now this is the mean position of the body, because now body is in rest state. So this is the mean position of the body. So for example, if we mark reference line, so this is for the reference throughout the experiment. So this purple line represents the initial mean position of the body. Now, for example, if we stretch the spring, so definitely spring moves towards right hand side. We have 1, 2, 3, 4, 5 loop, let's suppose. So in this condition, what happens? Body moves towards the positive side, and we also exerts force in forward direction, right?
Right. Okay.
So initially we can say displacement is zero, force is also zero, acceleration is also zero, right? But now we can say, let's suppose x, now displacement is changed and we got new displacement. Let's suppose that is equals to x naught, right? And we
Right.
also
Okay.
exert force on it. We will discuss about force and acceleration now. So for example, we got a new position over here, that is x naught in the positive side, And you know that when you stretch the body that is connected with the spring, so you always feel that a spring is also exerting a continuous force in opposite direction, right? Just like the rubber band.
Yeah.
When we stretch the rubber band, so we know that rubber band is also trying to exert force in opposite direction, and it also moves in opposite direction. Even like if we stretch it, so when we release, it moves in opposite direction. We stretch in towards right hand side, but when you release, it moves in opposite direction towards left. Okay, so that's why we always use negative sign, because force tries to move body in opposite direction, right?
Right, okay. So it's
So
like already completing one of like the
yes.
requirements for.
So basically, by itself, when body starts to move, when we release it, so it always moves in opposite direction. So minus F naught, and definitely the direction of force and acceleration both are same according to Newton's second law. So definitely acceleration also be in the same direction, right?
Yeah, okay.
Okay. So initially we stretch the body towards right hand side, and it reaches extreme position, like one extreme position to the right. And when we release the body, so again it passes from the center, from its mean position. Okay.
Okay.
So the third scenario will be like, so now body is passing from its mean position again. Initially body is in rest state, but right now body is moving towards left hand side, and the speed of the body is maximum. Maximum speed, body is moving with maximum speed towards left hand side. And in this point, like at this specific point, again, if we want to write all the things, so we can say displacement is in initial position, because it again reaches the same point, that is the starting point. So displacement is zero, right? From its mean position, because body is still on mean position. So that's why we are writing zero. Okay. And at this particular stage, force will also equals to zero, because when we stretch a spring, so then spring tries to apply force in opposite direction. But right now, at this specific point, a spring is in its normal position, because it is now at original length, just like we discussed in the first case. Okay,
Okay.
so that's why force is zero, because spring don't need to apply any additional force to overcome any external force. So that's why force is zero. Okay. And
Okay.
finally, what happens? Definitely, spring starts to compress because of the force and because of the acceleration. So final state like this. And now what happens? Now spring try to push body in forward direction, again in opposite direction. So that is positive. But right now body is in negative side, on the left side of the mean position, that is the negative side. So in this case, we can write minus x naught. Force is also in the positive side, like forward right hand side. Acceleration also towards the positive side, okay, towards right hand side. So this is the scenario for the spring mass system. Okay,
Okay.
this is the first screenshot of the motion, second, third, and fourth. And this process continue until the body again comes to its mean position or rest state. Okay, now
Until it like all of its energy, basically.
yes. So until it consumes all the energy and some energy waste in the surrounding, it continues to oscillate to and fro in the same scenario. And now we need to check either it is simple harmonic motion or not. So first of all, we need to prove it. So definitely we are going to start from the basic. We already studied about deformation in AS that is related to the spring constant. So from that scenario, we know that Hooke's law is equals to minus kx, minus sign again, opposite direction of the force for the spring. So F equals to minus kx. And we can also include Newton's second law of motion because there is also acceleration included. So these are the two equations. Okay. And now we can compare both equations because in both equations we have force on left hand side. So when you compare both equations, so it will be equals to ma equals to minus kx, or acceleration is equals to minus kx over m. Further, both k and m are constant quantities, right? K is a spring constant, mass is the m is the mass of the body, which is also constant, right? So it means we can also write this equation as, because if we remove constant quantities, it converts into directly proportional sign. Okay. Okay, so from this scenario of a spring mass system, we observe that a spring mass system also equals to the simple harmonic motion because calculation shows that it is exactly equals to the same formula that we discussed for a spring mass system. Sorry, for simple harmonic motion. Okay.
Okay.
Okay, and right now we have constant values k and m. So when we remove proportionality sign, it converts into the constant value. And for example, if constant values are given, so it converts back into the proportionality sign. Okay, so that is like a mathematical steps that we need to follow to drive the equation. And again, if we consider the original equation, this equation, so in this equation we also have constant, oh sorry, we also have proportionality sign. Now we need to remove this proportionality sign and we need to write a constant over here, right? So that constant is equals to omega x. So this symbol is actually called omega, not W. It looks like W, but it is omega. So basically this symbol represents angular frequency. A represents acceleration,
Okay, and then omega,
angular frequency.
what is angular frequency? Like I still don't get that.
Basically, in circular motion, we know when particle starts to move from zero, it starts to make a complete circle. So from zero, it starts to increase 10, 20, 30, 40, 50, 60, 90, 180, 270, 360, right? So that is a complete round trip for a circular motion. Okay. So in circular motion, we are using angles. So the frequency in circular motion is called angular frequency, right? Like there are linear motion also, just like we discussed in the wave. So we used to write number of waves passing through a point in a unit time is called frequency. So that is linear frequency in simple words. Angular frequency means we are actually measuring with the help of different angles. Okay. And we will also discuss how we link this angular frequency in the other concepts like simple harmonic motion in spring mass system, because in a spring mass system we know that there is no angle, it is a complete linear motion to and fro. But we will discuss in detail that how to merge this concept with related to the spring mass system and the pendulum also, right?
Okay, all right. So like when it's going, it's like when it's moving at an angle, like not it's not
Yes.
linear to like the x.
Yes, because simple harmonic motion is not only for linear, it is also for the other angular motions. So that's why we use this symbol, and we can compensate with some other quantities. We will discuss with each example that how to link with the other quantities with angular frequency. Okay, this is displacement. Okay, uh, so this is the scenario, and we also discuss one example. And before talking about spring mass system further, if we consider journal graphical representation for simple harmonic motion, because we got one example to understand the idea. So graphically, we can say we have x-axis, y-axis given. So in this graphical representation, we are taking acceleration on y-axis, positive and negative, displacement on x-axis, positive and negative. So if you consider this to and fro motion, so we observe that if you consider mean position, this is mean position at origin 0. So at origin, acceleration is 0. In a spring mass system, we observe that always at mean position, acceleration is equals to 0. But at extreme position, away from the mean position, we always observe that acceleration is maximum, right?
Okay.
So the graphical representation is very simple. We just need to draw a straight line like this, and it shows you maximum acceleration on both extreme positions, right? This is
Yeah.
positive one, and this is negative. And we observe the same thing. You can see when displacement is in the negative direction, so acceleration is in the positive direction. And it also confirms from the graphical representation, right? And for the other examples, just like we discussed one example, we will discuss simple pendulum example also. But before that, if we write down some common features of simple harmonic motion, so the features for simple harmonic motions are: first one, we used to draw a straight line. And it is also passing through origin. Number three, negative gradient. And the last point, it is also very important, equal amplitudes on both sides. Okay.
Okay.
So we also mark the same distance from the mean position on both sides. So these are four important points related to the graphical representation. It will also help you because sometimes they ask about graphical representation. So like there are 3 marks given, 2 marks given. So it will easy for you to identify that which points we need to follow for your graphical representation. Okay, next we have, now again if we compare spring mass system with simple harmonic motion. So last step we discussed that it is equals to this equation that is related to simple harmonic. Okay, now the problem is angular frequency, right? How to relate with the angular frequency. So this part is slightly related to the circular motion because in circular motion we already drive so many equations related to this angular frequency, right? So that's why in this topic we are going to use direct link with that quantity. Okay, it is equals to omega square. Okay, so now if we relate with the original equation of simple harmonic motion with this constant equation of spring mass system, so we can say that omega square x. So all quantities are same, only constants are different. Okay,
Okay.
so if we relate their constant values, so we can say that after comparing equations, omega square is equals to k over m. Or let's suppose right now angular frequency is not given, right? Angular frequency is not given in this scenario. So we can make it simple. You know that frequency and time period are inversely linked to each other, right? So frequency and time period both are inversely proportional to each other, like frequency is inversely proportional to the time period, the simple formula. So we can also relate angular frequency with the concept of time period like this. Omega equals to 2 pi because in radians 2 pi is equals to 360 degree, right? So if we are talking about one complete round trip, one complete cycle, so that is equals to 360 degrees, and 360 degrees is equals to 2 pi in radians, right? So 2 pi over time period whole square is equals to omega square also. So you can see it is very simple to substitute the values on the place of angular frequency in the equations. Okay. And now we need to just summarize this equation. It will be equals to 4 pi square over t square equals k over m. And if we make t as a subject in this equation, so t square is basically equals to 4 pi square m over k, right? And if we
Right,
use
okay.
Yes, if we use square root on both sides, because we have a square on t, so we need to like cut down this square. So we need to use a square root on both sides, and finally it will be equals to m over k, like this. Okay.
Okay.
So by using this equation, you automatically drives the formula for the time period of spring mass system. Like if you want to find out the time period for spring mass system, so this is the equation. K is constant value, right? Spring constant. Mass is the mass of the body. 2 pi is also a constant value. So very simple to calculate the time period, right? So
Right, okay.
practically, if you are performing this experiment, so you need to know about the mass of the load and the spring constant value, and you can simply find out the time duration or the time period of that spring mass system.
Okay.
So this is the example for a spring mass system. Okay. And in the same way, from a graphical representation, we discuss how to relate graphical representation. And the second example is about simple pendulum. Okay. So simple pendulum is the second example. So if you want to check that either simple pendulum is also simple harmonic motion or not, so you can also relate that example. Example number two, simple pendulum. So in simple pendulum, again, we need to mark positions for the diagram. So let's suppose, so let's suppose initially pendulum in this position, and for reference, this is the mean position. Just like the wall clock, when wall clock, we use the wall clock. So same pendulum is over there in the wall clock. So initially it is in rest state, completely vertical because of the gravity. But if you move left, right, so it will change its motion, and that will give you oscillations. And in second example, it will be in this direction. And in the third screenshot of the motion, it will be in this direction. And finally, it comes to its mean position again, and the reference points are still same, like this. Okay.
Okay.
Okay, so basically in simple pendulum, what happens, we take that sphere of the pendulum and we move towards left hand side, and definitely when we release this pendulum, so it starts to move towards right hand side, towards positive
Okay,
direction.
so first it was going like if it depends on which side you move it
Yes,
to.
exactly. So right now it is going to oscillate towards right then left. Okay.
Okay.
And same references we are using, this side positive, other side negative. So basically, When we take this sphere or this pendulum to the left hand side, so force exerts towards the right hand side, and still it is moving towards right hand side. So at this point we got maximum speed, and then it moves towards the other side of the mean position. But this time force exerts in the opposite direction, right? And finally pendulum starts to move in the opposite direction with the maximum speed again, right? So I hope motion is very simple to understand in this diagram. Okay.
This one, it's easy-ish.
Yes. And for example, if we consider the quantities in all positions, so for displacement, we can say it is equals to minus x naught, because we used to move the body in negative direction towards left hand side. But acceleration will be positive, same force. And in the second option, we have 0, 0 because mean position. And then in the next, we have positive side displacement, acceleration negative, and then 0, 0, right? Any confusion?
No.
Okay. Okay, right now we are working with simple pendulum, and we know it is not linear motion, it is angular motion. And in this angular motion, we need to consider the vector diagram, we need to make the components, right? So components are very important in this.
Okay.
So right now in simple pendulum, for example, this is our reference point, and from this reference point, pendulum initially in this position, right? And it is also making certain angle with vertical, right? And you remember in AS, if body is making angle with vertical component, so the horizontal and the vertical or the perpendicular components shuffles, right? So this becomes
Yeah. Is
W
okay
sine theta.
because of the angle,
Yes,
angular frequency. So we have to use sine.
exactly. And this component becomes
If it's
cos theta.
vertical, then we use cos, and if it's horizontal, then we use sine.
Exactly. And this is the original direction of the weight of the body. And this is the tension. Okay.
Okay.
So the other quantity that we left in this diagram is related to the force. So in the first position, we can say force is equals to positive W sine theta, then 0, then negative sine theta, and 0, right? So this
Oh,
is the representation for simple pendulum. Okay.
okay.
And according to this simple pendulum motion, we can say that W sine theta is acting as the restoring force, because this is the component which is with the motion of the pendulum. Okay. W cos theta is the component which is opposite to the tension. So basically tension and W cos theta are equal and opposite. Okay.
Okay.
So the only contribution in the motion of the pendulum is of W sine theta. Okay. So we can simply say that W sine theta is acting as restoring force that tends to bring the object towards mean position, right?
Right, okay.
So this is responsible for the motion, and we can further say that if theta decreases, sine theta also decreases. Force also decreases. Acceleration also decreases, right? So this is another factor we derive from this whole idea.
So the like okay, so if someone says if the angle is decreased, what would happen to the acceleration? So we'd say it also decreases.
Yes, because we got less displacement, and according to simple harmonic motion, acceleration is directly proportional to displacement. Angle is short, it means a small displacement, and acceleration will be also small. Okay.
Okay.
And finally, if we drive the equation, so we know that F equals to ma according to Newton's second law, because we exert external force on the pendulum to make it oscillate. And the force in simple pendulum is responsible, that is responsible for the motion, is W sine theta component, right? So W sine theta is responsible for the motion, and if you compare both equations, it will be equals to ma equals to W sine theta, and then it will be equals to W equals to mg, m cancel out each other, sine theta. And now, according to the sine theta, so if you consider sine theta is equals to perpendicular upon hypotenuse, right?
Yeah, okay.
So, in this whole diagram, so hypotenuse is the length of the thread in the diagram, right? And perpendicular is the displacement, right? So this quantity is the perpendicular from right angle triangle, because it is a right angle triangle, and this displacement sides represent perpendicular, and this length sides represent hypotenuse, and this yellow line represents base, right? So these are the components of right angle triangle. Okay.
Okay.
So we can say that sine theta is actually equals to x over L. Okay. And again, because of opposite direction, we use negative sign. And finally, we can say that G and L, these are the constant quantities into X, and it is also equals to simple harmonic motion. Okay. Right? Any question? Any confusion in this?
So what we first did was we did the force. We're basically like what's the word?
We are actually driving the equations from the
Yeah.
original situation given, original example given, and relate with Newton's second law. Okay.
So also like mass times acceleration, that's like that type of acceleration, and then mg is like the gravitational acceleration.
Yes.
And then we can cancel out the masses, so we're left with that. And then for sine theta, why do we do x over L again? Because
Because
that's
according
how
to
you
the,
do that.
yes, according to the diagram, sine theta is equals to uh perpendicular over hypotenuse. So perpendicular is equals to the side of the displacement, and hypotenuse is the side of the length of the thread. So that's why
And then
sine is equals to x
we
over
put
L.
negative x because it moved away
Yes,
from x,
exactly.
like to the right hand side. And I mean the left hand side. And then we just and then you what you did was you rearranged it kind of to
To
make
it
the
equals,
gravity inside of the bracket and the x outside.
because gravity
And
and length both are the constant factors, and it will help
okay,
you to use the directly proportional sign on the place of constant quantities. Okay.
okay.
And this is the proof of simple pendulum is also equals to simple harmonic motion.